Hey guys, hello everyone. I hope that I am audible to all of you. Right, so today in this particular session, we are going to take chemical kinetics. We are going to understand, basically, we are going to revise chemical kinetics. Okay, so in chemical kinetics, there are basically three parts in which the whole chapter is actually divided because it's a huge chapter. Okay, there are a lot of things to be discussed in this chapter. The first part is comes under the basic part, then we discuss about the enzyme catalysis, and one more part is there that is called as your transition state theory. Okay, so that's how the chemical kinetics is divided in. So I'm going to take the basic part today. Okay, I'm going to discuss about the basic part or the basic like terms or the basic equations of your chemical kinetics. We'll also take some questions and try to solve them. Okay, just a minute, let me just adjust quite a few things. Yeah, all right, so this is how this is going to be. So let's start with it. So why this chemical kinetics is so important? First of all, so it's one of the easy topic from your physical chemistry. The second thing is that it's very, like, you all are familiar with it, right? You might have studied this same topic since your class 12th or class bachelor's, like from your BSc onwards. So that's why you're quite familiar with this particular topic. It's a scoring topic as well. You get around like 10 to 12 marks from this in your CSIR-NET exam. And in CSIR-NET and in GATE exam, both generally your numericals are asked. Okay, so generally numericals are being asked over there, so you should be good at solving numericals. That's what is more important. So for that you need to know equations, and if you know all these equations, it is easier for you to approach. Okay, so as I was telling you, there are three parts. The first part is basic rate law equation, and also called as your Arrhenius equation, right? The second part is your enzyme catalysis, and the third part is your collision theory and the transition state theory. Okay, so that's how the like whole chemical kinetics goes by. You will easily get around 2 to 4 questions from these topics in your CSIR-NET exam, and you can score around 8 to 12 marks from here. Okay, what you need to know is how to apply a formula. That's more important to know. All right. Okay, so fine. We'll start the session now. So over here, which books are important to be followed? So basically, the book from your Puri Sharma and Patania. That's a good book to follow for this particular topic. Apart from that, you can also follow Atkins. Okay, there's a book by KL Kapoor for your numericals. Okay, so for numericals, you can go for this particular book. So that's how you can like prepare on your own. Okay, so I am going to tell you some important formula regarding your chemical kinetics in this particular video. So the basic thing starts from your rate law equation. Okay, the basic rate law equation. So a rate law equation goes like rate is equals to K A to the power Na and B to the power Nb, where this Na and Nb are basically order of the reaction. Okay, with respect to A, you have Na, with respect to B, it's Nb. Now there is a difference between order and molecularity. What's the difference? For example, if I have a certain reaction, let's say I have H2 plus O2, it's giving me H2O. Okay, if I just balance this equation, so this 2 over here correspond to the molecularity of H2. Okay, like the molecularity of reaction with respect to hydrogen ion, hydrogen molecule, and 1 is the molecularity with respect to oxygen. So in a balanced chemical reaction, the coefficients tells you about the molecularity, whereas for the rate law equation, like how does the rate depends upon the concentration of your hydrogen and oxygen, that depends upon your that is called as your order of the reaction. Now order and molecularity can be same or they can be different also, so it depends. Okay, it's a subjective thing. They can be equal also, they can be unequal also, so there are certain points about it. So like order is the sum of power of terms in the rate law equation, whereas molecularity is the number of reactant molecule which are shown in the particular step of the reaction. Okay, order is determined for overall reaction, whereas molecularity is determined for each step of the reaction. Then order is a experimental value, molecularity is a theoretical value, and order can be fractional 0 or it can be negative, whereas your molecularity generally is like it cannot be. Okay, it cannot be fractional 0 or negative. So that's what is about your molecularity and the order of reaction. Okay, now before going any further, let me tell you about the Revise India program, which is right now running on the Unacademy platform. So on Unacademy Plus, you get access, or you have an opportunity to revise all the concepts within the next upcoming few days. So it has been started from 1st of November on the Unacademy platform already, and it is running right now. Okay, so if you are interested in that, you can just log into the Unacademy app. Okay, on the Unacademy app, you don't have to take plus subscription, it's totally free. So you just have to go to the Unacademy app and you have to enroll yourself in the Revise India program, and you have to revise, like you have to just enroll yourself into the respective educators class. So in that case, you will get notified when a particular educator is going to take a free live session. Okay, my session is going to be there in the today's evening, that is at 9:30 p.m. today. So if you are interested in that, you can join me over there. Okay, the session is going to be on chemical kinetics, but the numericals will be taken in that session. So if you are interested, you can join it. All right, coming back to this thing, so let's now talk about the rate law expressions. Okay, so there are different rate law expressions for first order, second order, third order reaction. So for the first order reaction, this is the differential form. Okay, this is called as the differential form, and this particular form is called as integrated form, integrated rate law equation. Okay, that's what we call it. So for the first order, the rate constant K1 is given by 2.303 upon T log A initial upon A final. So A initial is the initial concentration, A final is the final concentration. Alright. For the second order reaction, it's given like the differential form is dA by dt is equals to minus K2A square, or the rate constant K2 is given by 1 by T in multiplied by 1 upon A minus 1 upon A naught, where 1 upon A is final concentration, okay, and 1 upon A naught is initial concentration. Good afternoon, Repula. Hi. So this is initial concentration. Alright, so that's how the rate constant is calculated. For different reactant, let's say for the second order reaction, I have two different reactants A and B. In that particular case, how the rate equation is going to be written? So it's going to be K2 is equals to 1 upon A minus B into T ln, that is log base E or natural log of B A minus X divided by A B minus X. Okay, what are A, B and X over here? So A is the initial amount of initial concentration of reactant A. Okay, so it's like this, A and B giving you product. So initially when the time is 0, at that time the concentration of A is taken as a small a, the concentration of B is taken as a small b, and when the time is some t, at that time the product is X amount formed, so it is A minus X remaining and it is B minus X remaining. So that's what is kept in the equation. Okay, for the third order reaction. For the third order reaction, the equation I guess is not visible to you. So the equation goes like this: K3 is equals to 1 upon 2A square T, and in the bracket we have X 2A minus X divided by A minus X ka whole square. Okay, so that's how we write down for the third order reaction. Alright, for zeroth order reaction, the equation is like K is equals to X upon T. Okay, or you can write down that K is equals to, this is the concentration of product. Okay, X is the concentration of product, or you can write down that K is equals to yeah, you can write it down in the terms of A also. Okay, next is your half-life. Okay, so yeah, one more thing is there, that generally all the catalytic reaction they follow zero order kinetics. Okay, this is something you have to note it down. Okay, it's a very important point. Next thing is half-life time. Okay, half-life time means the time required uh, for the particular reaction in which the final concentration becomes half of the initial value. That is what we call it as half-life time. Okay, for the first order reaction, the half-life time is given as 0.693 upon K1. For second order reaction, it's given as 1 upon K2A. For third order reaction, it's 3 by 2 1 upon K2A. For zero order reaction, it's A upon 2 K naught. Now for general equation, it is written over here, but I guess it's not visible to you, so I am writing here that T half for the general reaction. Okay, for any nth order reaction, T half will be written as 2 to the power n minus 1 divided by K n minus 1 and a to the power n minus 1, okay, where n will be the order of the reaction. You can put any value except for the first order reaction. For the first order reaction you have to memorize it. For all the others you can you can find out the equation directly by looking into this. Just put the value of n and you will get that. If you put n is equals to 2, you get it for the second order. If you put n is equals to 3, you will get it for the third order reaction, and so on. Okay, so that's how this particular half-life will be written as. Okay, next is some important point regarding your T half. The first point is that your T half is proportional to the concentration of reactant for zero order reaction. So if the reaction is of zero order, the T half is proportional to the concentration of reactant. Okay, that's what it is. Second point says that T half is independent of the concentration of reactant for the first order reaction. So for first order reaction, the T half does not depends upon the concentration of reactant. So whatever the concentration of reactant is, T half is not going to change. For the second order reaction, T half is inversely proportional to the concentration of reactant. That means that T half is inversely proportional to concentration of reactant for the second order reaction. So that's how it will be done. Now T half is proportional to the concentration to the power 1 minus n. So for any nth order reaction if you want, so it will be proportional to concentration to the power 1 minus n. Okay, so you can use this equation to find out relationship between concentration and T half for any order reaction. For first, second, third, any order reaction you can do it. For example, if you want to do it for first order reaction, put n is equals to 1, so it will become 0. So T half will proportional to this, anything to the power 0 will be 1. So T half will be independent of concentration. Okay, if you put 0 for n, so you will get T half proportional to A. That's what you got. If you put n is equals to 2, you will get A naught to the power minus 1. So that will be for the second order. Okay, now next thing is unit of rate constant. Rate constant is denoted by K, and the unit of K plays a very important role to identify which order reaction basically they are talking about. So for zeroth order reaction, the unit is moles per liter per second. For first order reaction, it's second inverse. For second order reaction, it's liter per mole per second. For third order reaction, it's liter square per mole square per second. For any fractional equation, it is given like this. Now a general equation is also there. So for any nth order reaction, it's given by mole to the power 1 minus n, liter to the power n minus 1, and seconds to inverse. Okay, so this is what we have for the nth order reaction. Okay, this is the unit for the nth order reaction. So just make a note of all these things. Okay, the next important thing is your Arrhenius equation. Arrhenius equation relates two important things, that is rate constant. Okay, rate constant was related to your temperature of the reaction. Okay, before Arrhenius equation, it was observed that with every 10-degree rise in temperature, okay, with every 10-degree rise in temperature, the rate constant doubles itself. Okay, it doubles itself. So this was observed. Okay, this particular thing was observed before Arrhenius equation. Arrhenius equation just gave it a proper mathematical equation. So it's given as K is equals to A e to the power minus EA by RT, where EA is called as your activation energy. Activation energy is the minimum amount of energy which is required for a particular reactant to get converted into product. Okay, so when a reactant is getting converted into product, it has to overcome an energy barrier, and that energy barrier is called as your activation energy. It's given like something like this. So if here is your reactant and here is your product, so it has to go through a particular thing, and that's what we call it as, like, this is the energy barrier which is here. Okay, now this energy barrier will tell you ki, like, activation energy. All right, so this is what it is. This particular energy difference is activation energy. All right, so good afternoon Amresh, hi. So this is reactant and this is product, and this is your activated complex or transition state. We'll talk about it later in the transition state theory. Okay, so now Arrhenius equation can also be written in the logarithmic form. It goes like log k1 upon k2 is equals to EA upon 2.303 R in the bracket 1 upon T2 minus 1 upon T1, or it can be written in the differential equation, that is del by del T of ln k is equals to EA upon RT square. Okay, so these are some important equations from the Arrhenius one. Now the next thing is graphs. Okay, the study of graphs. It's very important to study them because chemical kinetics is all about these things. So the equation, you know, for the zeroth order reaction, where EA must be positive. No, it's not that. Yeah, EA must be positive. Yeah, the overall value of activation energy has to be positive. Yeah. Okay, so yeah, I was talking about this, that the equation for the differential rate law equation, we have discussed all these equations for zeroth, first and second law, sorry, second order. Now the concentration versus time graph, if you plot, okay, for the zeroth order reaction, it goes as a straight line. Okay, why? Because this is the equation which we are using. So we are plotting this concentration versus time. So it can be written as y is equals to mx plus c. Okay, in this case you will see that the slope, okay, the slope which comes out is minus k, and the intercept which is here is a naught. Okay, so this particular value from here to here is basically a naught, and the slope is minus k. So that's how this equation came. If you go for the first order reaction, now the equation can be written like this. It's exponential decay kind of equation because e to the power minus kt is written. So we are plotting this versus this, right? So if you see this properly, this is called as an exponential decay kind of curve. So that's why the curve is decaying exponentially. Okay, this is concentration versus time. The next is for for the second order reaction. The equation is 1 upon A is equals to 1 upon A naught my plus KT. Okay, that's what the equation is. We are plotting this, we are plotting just this versus this. Okay, so it's these two things are going to be inversely proportional to each other. That's why the graph is going to be something like this. Okay, so it's like y is equals to 1 upon x graph. So it's like that. Okay, fine. So these three graphs are important. Next, the most important graphs are your straight line plots. Okay, so for a straight line plot, you should know that among which two things the graph has to be plotted, and what will be the slope of the graph and what will be the intercept of the graph. So this is for zero order reaction, this is for first order reaction, this is for second order reaction. For zero order reaction, the graph is plotted as concentration versus time. First order reaction, it's like ln of concentration versus ln of time. Ln of concentration versus time. And for the second order reaction, it's 1 by concentration versus time. Okay, so, and the slope for zeroth order reaction is minus k. The slope for the first order reaction is also minus k. Slope for the second order reaction is equals to k. From where did it came? So it came from this equation, that is a is equals to a naught minus kt. Okay, so from this equation we are plotting, since we are plotting this concentration versus time, so that's why the slope came as minus k, intercept is a naught. If I talk about the first order reaction, the first order reaction is something like this. It goes like yeah, so the first order reaction is this, that is 1 upon not 1 upon, it's like ln a naught or ln a is equals to ln a naught and minus kt. Okay, that's the equation which we have. So here we are plotting this on the y-axis and this on the x-axis. So that's why slope is minus k and the intercept is ln a naught. Okay, so remember the intercept over here is ln a naught. Okay, and the intercept over here is just a naught. Okay, the second order reaction is basically, we have seen the reaction, it's 1 upon a is equals to 1 upon a naught plus kt. Okay, that's the equation. So we are plotting this 1 upon concentration versus time. So here the slope becomes plus k and the intercept over here is 1 upon A naught. Okay, so these are the three straight line plots, and you should be aware about them. Okay, that what are the things which you are going to take. Half-life is given to you as the equation we have already seen, and the unit of rate constant also we have already seen. Okay, so we'll go for the next thing. The next thing is about the some important graph again. So for the rate versus concentration plot, if you are doing, so if you are plotting rate versus concentration, if you are plotting for the zero order reaction, you will get a parallel line, okay, a constant line. For the first order reaction, you will get a straight line with a zero intercept. Okay, for second order reaction, you will get a exponential exponential increase. Okay, it's not decay, it's exponential rise kind of curve. Okay, then if you are plotting concentration versus time, we have already seen that for zeroth order reaction you get a negative slope, for first order reaction you get a exponential decay curve, for second order reaction it's again y is equals to 1 by x type of graph. The next important thing is for your Arrhenius equation, okay, graphs related to Arrhenius equation. You know Arrhenius equation was given by this k is equals to a e to the power minus a by rt. The equation can be reduced by taking ln both sides. So if you take ln, so it became ln k is equals to ln a plus ea upon rt, right? That's what you have. Or you can write it down like this, that ln k is equals to minus ea upon r into 1 upon t plus ln k. This is the plot wise approach. Okay, the plot wise approach is given to you. Now you can see over here that ln k versus 1 upon t is what we are going to plot. The slope which we will get is minus ea upon r, and the intercept from here to here is basically ln a. Okay, where a is your pre-exponential factor. Okay, you can also have a graph in versus like k versus t. Okay, you can have k versus t graph. T is the temperature, k is your rate constant. In that case, you will get a logarithmic graph. Okay, the graph is logarithmic graph, and it's showing you a like increase in the graph with the increase in temperature. Okay, fine. So these were some of the important questions which can be asked based, like, sorry, some important formula which are important to be discussed from your like on the basis of your basics of kinetics. Okay, let's take some of the question and try to solve them. Okay, here we'll take this one. It says that if the rate of a reaction are R1 and R2 at concentration C1 and C2 of the reactant respectively, the order of the reaction n. Okay, they are asking what is the order of the reaction. This is also basically one of the equation, okay, which has been asked in the question. So you have to derive it, or you have to tell that how it will be done. So let's say that the rate is equals to concentration to the power n. This is what we get from the rate law equation, right? So R1, if I have R1, so R1 will be equal to concentration to the power n, C1 to the power n, and R2 will be equal to C2 to the power n. If you divide both of them, so R1 upon R2 will be C1 upon C2 whole to the power n. You can take log both sides, so that is going to give you log R1 upon R2 is equals to n times of log C1 upon C2. Now just if you want to take n, you can take this to the other side, and you will get log R1 upon R2 divided by log C1 upon C2. Now here I am going to use the property of log. You know that log A upon B can be written as log A minus log B. So same thing I am going to do. So what I can write down is n is equals to log R1 upon R2 can be written as log R1 minus log R2 divided by log C1 upon C2 can be written as log C1 minus log C2. So this is going to be one of my equation, okay, which can be asked and which you should know. So if you look upon the options, which option is correct? So option number first is the correct option for this particular question. All right, so I hope this is much clear to you that how it has been done. All right, let's take the next question then. The next question says that for a reaction, the reaction is given to you as 2A plus B is giving you 3Z. The rate of consumption of A is 2 into 10 to the power minus 4. What is the rate of formation of Z? Okay, that's what they are asking. So let's use the rate law equation. So I guess it is solved. Yeah. So yeah. So the equation is given as 2a plus b is giving you 3z. So with the, if you want to write down the rate, so with respect to a, it will be dA by dt. Whatever the coefficient is, you just take it in the denominator. So if it is 2 times of a, it will be like 1 by 2. The minus sign says, or minus sign tells you that a is in the reactant side. Okay, so minus sign tells you that it is a reactant. That's why we have negative sign. Okay, b will be dB by dt, and minus sign shows that it's on the reactant side. Since there is no coefficient, so nothing will be taken in the denominator. Z is on the product side, so dz by dt, the coefficient is 3, so 1 by 3 is written. Plus sign shows that it's on the product side. So remember this, minus sign for the reactant, plus sign for the product. You just have to relate this and this, that's all. Okay, because you are given with the rate of formation, rate of decomposition of this, and you have to find out the rate of formation of this. Now dA by dt is going to tell you the rate of consumption of A, whereas dz by dt will tell you rate of formation of Z, right? So that's what it is. Now if these two things are there, so this is what is needed to be calculated, this is what is already given to you in the equation. So the value of consumption of A was 2 into 10 to the power minus 10. So I'm going to use that 2 into 10 to the power minus 4. Solve this, so this and this will get cancelled out, you will get 3 into 10 to the power minus 4. So your correct option comes out to be option number 1. So this is how you have to use like basics of your chemical kinetics to solve these types of question. Alright, we'll go for the next one. Okay, the next question says that for the reaction with activation energy of 49.8 kilojoules per mole, the ratio of rate constant at 600 Kelvin and 300 Kelvin is, okay, is approximately. So they are asking that what is the ratio of 600 by K 300. Okay, so remember that if it is so here the temperature is 600 taken, and here the temperature is taken as 300. You know the formula that K is equals to A e to the power minus EA by RT. If I take ln both sides, so it was ln K is equals to ln A minus EA by RT. If I take it for the first one, so K1, A will remain A only, so activation energy will be EA1 and T1. Okay, and for the second one, I'll write down it like this, that is ln, because activation energy will be same, it does not changes with the temperature, so let the activation energy be same. Okay, ln K2 will be equal to ln A minus EA upon RT2. If you divide both of them, or if you just take subtraction of both of them, so that is going to be this. Okay, we have done it over here. So if you just take subtraction of both of them, you are going to have ln K2 minus ln K1 is equals to, this part will get cancelled out in both of them, you will get minus EA upon RT2, and minus will make it plus EA upon RT1. Okay, so you can take basically, yeah, log A minus log B can be written as log A upon B. So that is what is written as K2 upon K1. EA upon R is taken common from here. Okay, EA upon R is taken common from both sides, and in the bracket it will be remaining as 1 upon T2 minus 1 upon T1. If you solve that, you will get T2 minus T1 upon T1 T2. This is from the Arrhenius equation which we have just derived. K2 value is given as K600, K1 value is given as K300, and that's how T2 will become 600 and T1 will become 300. So just substitute all the values in the equation. So ln K600 upon K300 will be equal to 49.8, because activation energy you have to put, and that was given in kilojoules, so you have to convert that into joules. So 49.8 into 10 to the power 3 to convert this into joules. Okay, then R value was given to you in the question that you have to take it as 8.3, so take it as 8.3, and in the bracket it's going to be 600, because that's T2 minus T1 is 300 divided by 600 into 300. So solve everything, and you will get just 10 here. So if this is so, if you have, let's say, ln A is equals to x, so basically A becomes e to the power x. Okay, so in the same way, this whole thing, ln whole thing is equals to 10, so this whole thing will be equal to e to the power 10. So that is going to be your final answer. So the final answer comes out to be e to the power 10. That's how it has to be done. All right. Okay, fine. So let's take one more question and let's try to see how to solve it. Okay, let's try to do this one. It says reaction between A and B is carried out for different initial concentration and the corresponding half-life time are measured. The data is listed over here. The rate can be represented as. So you have to look for this and you have to say, you have to tell or you have to discuss that how the rate has to be, like what is going to be the rate of the reaction. Fine. So you can see that the T, if I just look for, you have to go for those two reactions where A is constant. So if I'm looking for these two reactions, let's say these two. Okay. So A is constant here. Now reaction will not depend upon A. It will only depend upon B. Now you can see that the concentration is getting doubled, right? From 10 to 20, you are getting doubled concentration. But the T half is not changing. Okay. There is no change here. So what does that mean? It means that the T half does not depend on concentration of B. That's what you can say. Or you can say that T half is independent of concentration of B. If it is independent of concentration of B, what kind of reaction it will be? So it will be first order reaction. Okay, this will be first order with respect to B. So B के respect में this reaction is going to be a first order. Alright, so you can simply cancel out option number 4 because here the reaction is given second order with respect to B, and you can cancel out option number 2 also because here B is not written. So that means it is 0 order with respect to B. So you can just cancel out that. Okay, now the next reaction you have to take where B is constant. So these two reactions I am going to take where B is constant now. So now the reaction will only depend upon A. Now if you see the reaction from here to here, the concentration of A is getting doubled. From 10 to 20, the concentration is getting doubled. What is happening to T half? It's becoming half. The T half is getting half. So what you can see that when you increase the concentration, the T half is decreasing. So what is the relationship between these two? So you will say that T half, good, very good, Reti. T half is inversely proportional, proportional to concentration of A, or you can say that reaction is second order, second order with respect to A. So second order with respect to A and first order with respect to B. So correct answer should be your option number 3. Okay, so this is how we have to do. These types of questions are very simple and they are generally asked in your CSIR-NET exam. They are also asked in your IIT JAM exam, also in your GATE exam. So you should be aware about that how to solve these types of question. Alright, so I guess we'll keep this much for this particular session. In the further session on chemical kinetics, I will take enzyme catalysis and the transition state theory. Those two things are there in the chemical kinetics. We'll discuss that in the upcoming sessions. Okay, before ending the session, I'll once again tell you about this Revise India program, which is right now running on Unacademy platform. So if you are interested, if you want, you can join this particular like Revise India program on the Unacademy platform, and the classes are totally free. My classes are also running over there. Today I have a class on numerical approach of chemical kinetics. Okay, so you can just go to the Unacademy profile, Unacademy app, and you can search for me, that is Noorul Huda, and you will get my profile over there and you can just enroll into the class. The class timing is 9:30 p.m. Alright, so that's what it is. So participate in this particular Revise India program and take the best benefit of it. Alright, okay, so thank you so much for joining live, those who have joined live. So my classes will be every Sunday. Okay, so I'll be taking classes on Sundays, and the class timing will be from, like, it usually has to be from 1 p.m. but now the class timing will be changed. It will be from 2 p.m. onwards, okay, on every Sunday. So that's how the classes will be. Okay, take care guys, and I'll see you in the next session. Bye bye.